Welcome back. This is the last part of the video, and then in this video we are going to look at the heat transfer between two black bodies separated by non-absorbing medium. In the previous sessions we have learned how our intensity is related with the emission power of the black body. For the diffused surfaces where it has the irregular surfaces, then it follows the Lambert cosine law, which is actually I equals to In cosine of theta. So if I try to give some details on this, then if we have the surface like this, and then the intensity of the radiation, which N is the intensity of radiation normal to the solid angle, okay. This is the intensity of the radiation which is normal to the solid angle. Then if this is the case where our solid angle is this one, then if we want to find any intensity at any direction, like this, for example, my intensity of I, which is having angle of theta, then I can use this Lambert cosine law to find I equals to In cosine theta. Okay. So this is the key for the previous video. Now what we are going to find is the heat transfer between the two black holes separated by the non-absorbing medium. So heat transfer, also you can say radiation exchange. Okay, radiation exchange. Okay. Now you have to keep in mind the definition of the black bodies. Now what I'm going to do is I'm going to consider this figure, that we have a large body here, black body. You can treat this as black body 2, okay, and in this having the area of A2. So in this I'm going to consider a very small, okay, or differential area of A2 like this. Then I'm going to consider another black body which is like this, and then this black body is having area of A1, and then I have, this is black body 1, and then I will also consider a very small differential area, you can say as dA2 like that. And they are separated by a non-absorbing medium. So I will say like they are separated by a non-absorbing medium. We have this medium here, and then I will say it has a distance of L. Yeah. Okay, all right. Now what I'm going to do is I will now write or draw the normal of the dA2. So how do we write the normal of the dA2? For example, we have an area of A like this. Area. How do you write the vector which is normal to this area? Then you try to assign some sign like this. Then you try to curl your finger, and then wherever your thumb is pointing is the direction of the vector, right? If I do that, then my area vector will point like this. So this is actually my small area vector. Like this, here the differential area has the normal area of like this, normal area vector of dA1, 2, okay? Then my differential area 1 has area vector which is the normal like this. And then let's say that they are making the area angle of beta 2 like this, and angle of beta 1 like this. So you have to note that this angle beta 1 and beta 2 is the angle between the normal that you have written, which is falling on the differential area, and the direction of your L. that you have signed your L, right? So it is the angle between the direction of the L and the vector which is the normal of the area. Now let us find the intensity. Okay, so from this black body 1, the intensity which is emitted will be directed in this direction. So you can say IB1, which is the intensity which is directed towards the body 2 from the body 1. In the same way, you can say the intensity which is directed towards the body 2 as IB2, which is the intensity of the black body 2 which is directed towards the black body 1. So you can say let IB1 be the intensity of black body 1, then IB2 be the intensity of black body 2. Now what I will again do is that here right now the direction of my normal, which is dA1 vector, is this side, right? Now what I will do is I will shift this and then I will do a vector resolution such that my dA1 here, my vector dA1 points to this direction. Okay, so what should I do? Any area, you can say this is dA1 dash is here, is the area which is projected towards this line, which is the along the L, which is separating between two medium. To do that, we get that. So from this relation, what we can do is here this is dA1, right? And then they have point here as differential area like this, and my required area is this one, dA1 dash. So they are separated by the angle beta 1. So how can I express this dA1 in terms of this one? Well, you can say I can write a right angle triangle, and this is opposite, so adjacent. So I can write dA1 dash equals to dA1 cosine of beta 1. Similarly, for this black body here, this black body, this is beta 2. So when I direct this vector here, dA2 dash, in this direction, in this line, then my expression for this is dA2 dash equals to dA2 cosine of beta 2. So what you are doing is, right now your area vector of dA1 and dA2 is pointed somewhere else, okay, which is normal to the surface area, differential surface area. But I want to project this such that this area vector is pointing towards this direction of which is joining my two bodies. Therefore, I get this two relationship, and it's very important to keep in mind. Now let us recollect what is the definition of intensity. So from the definition of intensity, we got that intensity of black body 1, okay, is actually the emissive power of the black body 1 divided by the solid angle subtended, okay, the solid angle subtended by 2, body 2 to 1. So by definition of intensity, I get that IB1, which is intensity of the black body 1, can be written in terms of the emission power, right? In the previous video, we say emission power of 1 divided by the solid angle which is subtended, okay, by 2 to 1. So we can say 2 to 1 like this. So actually what happens is that this is both the black bodies, right? So whatever emission this black body 1 gives will be absorbed by the black body 2. And then whatever emission that black body 2 gives will be absorbed by the black body 1. Therefore, the total net heat transfer will be the difference of the both. Okay? So our main thing in this video to find is this one. Net heat transfer equals to total energy emitted by black body 1 and absorbed by black body 2, okay, minus total energy emitted by black body 2 and absorbed by black body 1. So this is the key, okay, this is what we are going to find. So to do that, in order to get this, we have to invoke the definition of intensity such that we have to find this emissive power, so which corresponds to the total energy. Okay, now from here we got this for the black body 1. So for the second black body, which is IB2, intensity of the black body 2, this intensity of black body 2 by definition is emission power of the black body 2 divided by the solid angle subtended by the body 1 for the body 2. So you can say subtended by the body 2 by the body 1, okay, like this. Now our job is to find what is the expression for this one. So by definition for solid angle, we get that the solid angle like this is the differential area divided by the radius of the circle, right? So it is the definition for this one, because solid angle is defined for the spherical coordinates. So this dA is the differential area that we have found for the sphere, then we are dividing by its radius square. So if you treat like this as a differential area from this body, then your radius here, your R value is equals to L, okay? So therefore, in terms of R, you will use L. Now, to find this dA 221 first, this one, which is the solid angle, okay? The solid angle subtended for 2 by 1. Subtended for 2 by 1. So to do that, I will get the differential area. What is the differential area which is subjected to this? This differential area is actually dA1 dash here, right? So dA1 dash indeed is actually dA1 cosine beta 1. Therefore we have dA1 cosine of beta 1 divided by L squared. Same thing, d omega of 1 2, which is the solid angle subtended by 2 4 1, is dA2 cosine beta 1 beta 2 divided by L squared. So this is the expression for this. Now, how is this relevant to our intensities? You know, your intensity IB1 is given by the differential area dA1 cosine beta 1, which is directed towards the body 2 through L, right? So when you try to count how many radiant energy is passing through the differential area, then you have to calculate what is the area which is subtended by the body 2 for the incoming rays that to be absorbed by the body 1. Therefore, this becomes relevant in our IB1 term. Okay? Whereas for IB2 term, now this is the intensity which is given by the black body 2, right? So this is the intensity which is given by black body 2, and then our rays will shine like this towards the black body 1, differential area black body 1. So in order to count how many rays are passing through the differential area such that to strike on this dA1, the differential area should be given by our differential area 1. Therefore, this differential area, this one, solid angle subtended, should be given by dA1. So what is the solid angle subtended by dA1 for dA2? It is this one. Therefore, we have the energy, which is actually this one, dE1. So you can say dE1, which is actually the radiant heat flux, radiant, you can say radiant energy emitted by dA1 and striking on dA2. As you can see, dE2 is radiant energy emitted by black body of radiation dA, differential area dA2, and striking on dA1. Striking on dA1. Okay, it is striking on dA1. Therefore, how can we write the expression for this? You know that dE1, this is actually heat flux, right? Heat flux. Heat flux means the heat or the energy, flux means something divided by area. So this one, what I will say is, this dE1 is dE dash divided by, what is the heat flux for this? The heat flux for this is that dE1 by dA1 dash, right? So I can say dA1 dash equals to, what I'm getting, IB1, black body 1, times dA1, angle subtended to 1 by 2. This is what I'm getting. Now from here, what I will say is, this is actually dE dash divided by dA1 cosine beta 1, right? This dA1 dash is cosine beta 1 equals to IB1 1 to 2, like this. Okay, therefore this dE dash is what now? This dE dash, when I move this, will again say is a heat flux moving from 1 to 2. So I can say this dE dash 1 to 2 as dQ, okay, which is the rate of heat transfer or rate of energy transfer as it travels from the body 1 to 2, will be equals to IB1 cosine beta 1 area of 1 times d omega of 1 to 2, like this. Where now, as I moved this area term here, now this equation is just the heat transfer rate, which will now be watt. In the previous thing, it was watt per meter squared. Okay, the same thing for 2 to 1. So the 2 to 1, in order to get that, this one, my body 1 should give the solid angle such that I can count the emission power which is falling to the area which is subtended by the solid angle which is given by 1. Therefore, I can say dE dash 2 to 1 will be, now I am saying dQ of 1 to 2, sorry, 2 to 1. Now the radiant heat transfer which is from body 2 to 1 will be I times the B2, which is the intensity of the black body 2, times what is the angle, which is cosine beta 2 times d omega, okay, which is the area subtended on 2 by 1. Therefore, you can say on 2 by 1. So this expression is what now? This expression is I b2 cosine beta 2 times d a1 cosine beta 1 by L squared. Okay, times, now what is left here? From here you can also write this as, now I will express this in terms of the angles. Okay, now I will say I b1 cosine beta 1 dA1 times what is this? D omega, which is subtended to 1 by 2, is dA2 cosine beta 2 upon L squared. Okay, the same thing here is now dA2 is left. Okay, so this is the expression for the radiant heat. Now you have to keep in mind that this is actually emitted by black body 1 and absorbed by black body 2. Okay, this is the radiant heat transfer rate, which is emitted by black body 1 and absorbed by black body 2. Similarly here, this is actually emitted by black body 1 and black body 2 and absorbed by black body 1. Absorbed by black body 1. Okay, so actually here heat transfer rate means energy per second. So how much energy, heat transfer energy, is emitted by black body 1 and absorbed by black body 2 is given by this, and then how much heat per second or how much radiant energy per second is emitted by black body 1 and absorbed by black body 2 and absorbed by black body 1 is given by this expression. Now what is the punchline here? The punchline is this one. The net heat transfer will be total energy emitted by black body 1 and absorbed by black body 2 minus total energy emitted by black body 2 and absorbed by black body 1. So by these two expressions that we got here, this expression and this expression, we can now get the net heat, right? So the net change in energy between these two black bodies that you will see is dQ12 will be just the difference of this. So you can say I B1 cosine beta 1 area 1 times dA2 cosine beta 2 upon L squared minus I black body 2 cosine beta 2 dA2 times dA1 cosine of beta 1 by L squared, like this. Now by collecting the common terms, we will get now as cosine beta 1 cosine beta 2 dA2 dA1 by L squared and intensity of the black body 1 minus intensity of the black body 2, like that, which is our total heat transfer. Okay, for the differential area, which is dA, okay, this very small area of dA, here is dA2 and this is dA1. Okay, so this is the area, this is the energy transferred between this very small area that we have considered dA2 and is dA1. Now, you know that we have derived very nice expression for this intensity, right, last time. So what we got is that from the last result, our intensity times pi was what? The intensity times pi was actually the emission power, right? We have got this relationship in the previous video. So what about this one? The original equation is actually E equals to I n pi, right? Where what is I n? It is the intensity which is directed normal to the solid angle. Okay, so how is this relevant to our diagram? You can say that previously your area vector was this. So when I subjected here, I have intensity of the black body as IB1, right? But if you see very carefully, this IB1 is actually directed from our DI1 dash. So they are actually in the same direction, right? They are normal in the direction. Therefore, you can say that this IN is indeed IB1 and IB2, because the area that I am concerned is my DA1 dash and DA2 dash. So these are the solid angle which is in the same direction as our intensity direction. Therefore, we can modify this intensity term by using this expression. So our IB1, I can write this IB1, which is intensity of the black body 1, will be emission power of the black body 1. You can say black body 1 divided by pi. The same thing is intensity of the black body 2, you can write as emission power of black body 2 divided by pi. Now, what is the emission power of the black body? You know E1 and E2 that we have derived in the previous video, that our emission power of the black body is obtained by integrating our Planck's equation, right? So when we integrated, what did we get? We got the emission power of the black body was actually sigma times T raised to 4. So this is actually the Stefan-Boltzmann law. So if I say that my black body is at the temperature of absolute temperature of T1 and my black body is at the absolute temperature of T2, then I can write this equation now as sigma times T1 to the 4th power by pi equals to sigma times T2 to the 4th power divided by pi. So what you have observed is that these equations are very handy, okay? It will come any time of the derivation, so you have to keep in mind. So from here, by writing in this term, now you can rewrite this term here, right? You can rewrite this term in terms of our Stefan-Boltzmann's function. Yes or no? Yes, right? Now we have is dq1 to 2 equals to cosine of beta 1 cosine of beta 2 dA1 dA2 upon L squared times, what is common here? I can take sigma by pi as common, and I can see T1 to the 4th by T2 to the 4th, like this, right? So this is actually the heat transfer rate for the small differential area of dA1 dash and dA2 dash. Now I want to evaluate the total heat transfer, which means I have to evaluate this whole heat transfer of the whole area of the black body, which is A1 and A2, right? So what should I do? If I integrate this whole equation from with the A1 and A2, then I can get the whole heat transfer, right? So I can say dq1 to 2, if I take this integral, I will get q1 to 2, which is the rate of heat transfer between the body 1 and body 2, which is summed at whole area of A. So with this I can say these all are constants, right? So I can take it as pi sigma by L squared by T1 raised to 4, T2 raised to 4, and this one we have is two areas, which is A1 and A2. Then we have to find this as cosine of beta 2, cosine of beta 1, area of 2, area of 1, like this. So this will give you the expression for whole of the heat transfer rate, which is evaluated at the area of A1 and A2, the total heat transfer rate. So this equation will give you total heat transfer rate, or you can say total energy transfer rate, like this. Okay. Now let us see what is the energy which has been transferred from 1 to 2. Okay. Our next job is to find what is the total heat which is transferred from body 1, black body 1, and which is absorbed by the black body 2. So we have the heat transfer which is at a small differential area of A in this fashion, right? So to get the total heat transfer, just we have to integrate this, right? So when we integrate this, what we are getting? So we are saying total heat transfer. Okay, we are calculating this total heat transfer now. When I say total heat transferred from 1 to 2, or the total energy transfer from 1 to 2 is just integral of dq 1 to 2, like this, which I will get is by integrating this, and I have I b1, right, times dA1 times cosine beta 1, then I have dA, this one, subtended for 1 by 2. So just I have to integrate this whole thing here, like this. When I do that, you know, I have to integrate this in the 2 regime, because my dA12 is what? My dA122 will be dA2 cosine beta 2 upon L squared, right? So we have both the areas, so my equation will now shift to the double integration. So to do that, I will give now I b1, like this, times integral of a1 and also integral of a2 will be the whole thing, which is cosine beta 1 cosine beta 2, then you can say dA2 dA1 divided by L squared. This whole thing is actually my Q1 to 2, like this. Now just modify this, which is intensity of the black body 1. So intensity of black body 1 is given by emissive power of the black body 1 divided by the pi, right? So we have got this relationship from the previous video. So by doing this, you again know that emissive power of the emission power of the black body 1 can be given by the Stephen-Boltzmann's law, like this, T raised to 4. So by doing all of this and substituting, we are now getting as sigma T raised to 4, right? And our whole thing here is A1, A2, cosine beta 1, cosine beta 2, dA2 dA1 upon, here pi, we have this pi and L squared, which is Q1 and 2. Now, what is the total heat which can be emitted by the whole area of A1? Okay, so this is equal to the emission power of the black body, right? Because we have treated this as black body. So emission power of black body 1. So this emission power now we can say is Q1. Okay, so which is the radiant heat, total radiant heat which can be given by the surface. Okay, is equals to sigma times T1 raised to 4 times A1. So this is the one. So what is the difference between this and this now? You have to note that this is the fraction of energy transferred from body 1 to 2. And then from where? From this one. Because the total heat or the total energy that the body 1 has by virtue of being at temperature 1 is actually this much, right? From here only this much portion is radiated to the body 2 and then absorbed by the body 2, right? Now what I'm going to do is I'm going to divide, okay, this one here, Q1 to 2 upon Q1. What does it mean? This is the fraction of the radiant energy which is being transferred from body 1 to 2 to the total heat, okay, the total reservoir of the heat which my body 1 has. I will now get sigma T14 like this. Then I have is this A1, A2 thing here. Then cosine of beta 1, cosine of beta 2, dA2, dA1 upon pi L squared times, I have to reciprocal this, right? This one. So I will get this 1 divided by sigma T1 to the 4th and A1. So from here I can cancel this and cancel this out, and I am now getting is just 1 by A1 of the whole thing. So this is called as F of 1 to 2. Okay, this is the new term now, and this term is called the shape factor. Shape factor of 1 with respect to 2. So this is actually my Q1 to 2 upon Q1. So this is the ratio of the heat transferred out of the reservoir of heat Q1. Okay, so which is actually F of 1 to 2. The same thing I can do it for the body 2, right? This is for the body 1. For the body 2. Body 2 again, what do I have? My heat transferred by the body 2 to the body 1 and which is absorbed by the body 1 is just dQ221. Okay, is this one. So what I will do is I will integrate this, which is equals to, what is the expression that I have? So I have to go here and say 2 to 1 is this one. This is actually IB2 cosine beta like this, right? So I can write this whole as IB2 again A1 A2 cosine of beta 2 cosine of beta 1 dA2 dA1 upon L squared. The same thing I will do this dIB2. This IB2 black body 2 can be written as black body 2 upon pi, and my E2 will be what? The emission power of the black body 2 will be sigma of T2 squared, because my body 2 is at the absolute temperature of T2 here. So by doing this, What am I getting now? This whole thing is now sigma t2 to the power 4th and a1 a2 pi l squared cosine of beta 2 cosine of beta 1 dA2 dA1 like that. So the same thing I will do is, what is the total heat that my body 2 will have? Will be actually my sigma times A2 times T2 to the power 4, right? So I can also define the shape factor for this body 2, which is Q221 upon Q2, which will be shape factor of body 2 with respect to body 1 will be now, just it will be same thing, area 1 area 2 of cosine beta 2 cosine beta 1 dA2 dA1 upon pi l squared, right? So from here, this is actually again the shape factor. Okay, this is shape factor of body 2 now with respect to body 1. So this is the main thing that we have. The next thing that I'm going to do is that I have this one here, Q122 and Q221 here. So I have is now Q122 divided by Q1 equals to shape factor of 1 to 2, which implies Q1 to 2 equals to shape factor of 1 to 2 Q1. And the Q1 can be written as shape factor of 1 to 2 times sigma T1 to the 4th of area of 1. Right? The same thing you can write is Q221 upon Q2 will be f of 2 to 1 equals to, implies 1 equals to f of 2 1 Q2 will be f of 2 to 1 sigma T2 to the power 4th and area 2. Now the next thing I want to do is, I want to observe this equation very, very carefully. These two equations. Okay? So if you see this very carefully, what you are getting now? You are getting is that if you say that this, the whole thing is actually your F1 to 2, right? And then this whole thing, where is that? This whole thing is actually F2 to 1. Now I want to take the equation as like this. I want to say that f of 1 to 2 times a1. What am I getting here? F of 1 to 2 times a1. Then I will get is all of these equations, right? So this will be just equal to a1 a2 cosine of beta 2 cosine of beta 1 dA1 dA2 by pi l squared. The same thing I can do for this equation here. I can say f of 2 to 1 will times a2 will be a1 a2 cosine beta 2 cosine beta 1 dA1 dA2 upon pi l squared. So if you see this equation and this equation, if you see this equation, okay, you know that these two are equal, right? Then this should hold true that my f1 to 2 times a1 equals to f of 2 to 1 times a2. This one should hold true. So this is called the reciprocity theorem, which is reciprocity theorem. So this reciprocity theorem says that these two shape factors, they can be exchanged, or they are numerically equal for both of the bodies, which means if you find, if there's two bodies here, right, body 1 and body 2 here, see, and you have found the shape factor of body 1, which is body 1 with respect to 2, then you need to have to invest your hard work to find the shape factor of body 2, because this is related by the equation like this. So you can also say that my f2 by 1, if this f1 by 2 is known, then I can write this as f1 by 2 a1 upon a2, right? Which means you can interchange this by using the expression of like that. So what is now finally the total heat which is transferred by the body? So the total heat transferred by the body, which is my Q1 to 2, okay? So which is my Q1 to 2 will be now. Earlier, what did we get here in the earlier one? The earlier one I got is this equation here, right? So actually this whole thing is actually the shape factor, if you observe very carefully now, right? So Q1 to 2, the whole factor Q1 to 2 here, Q1 to 2 is now sigma T1 to the 4th T2 to the 4th times area of 1, right? The total heat transfer, which is total heat transferred between area A1 and A2, or you can write this F1 2 times F2A. You can write this using this expression and say my total heat 1 to 2 will be sigma T1 to the 4th T2 to the 4th times A2 times F of 2:1. So this is the last expression that I'm trying to find. And then now you have to know that this factor, they are purely geometric factor, right? It is a view factor, or you can say shape factor. Therefore, for the different shapes and different configuration, these values will be different. For example, there are charts for two parallel black body plates like this, where they are having the separation of L, and then they will have X and Y like this. Then they will have the shape factor for the chart. Okay, they will have the chart for the shape factor that we will discuss in the class. I hope you have understood this video, and I'll see you in the next class. Thank you.